Hey everyone! Today I want to talk about a little rotational physics problem. So in this example, we have a yo-yo which is made of two disks. One inner disk of radius little r, which is attached to this outer disk of radius big R. Alright? Around the little disk is an infinitely thin string of length L. This means that the inner radius is constant because we're considering the string to be infinitely thin. Now, we're going to go ahead and hold the string, and we're going to drop the yo-yo. Naturally, at the end of this drop, the yo-yo is going to be spinning with some speed, omega final, and it's going to be falling with some speed, v final. The goal of the problem is to determine the final rotational speed of the yo-yo after the string has completely unwound. Note that the yo-yo does not slip as the string unwinds. I want to start by making a little free body diagram where I label some of the forces acting on this yo-yo. So very clearly, we're going to have mg, which pulls the yo-yo down, and we're going to have the frictional force between the string and the yo-yo, which I'll label little f. Now, we can tackle this problem using conservation of energy if we prove that the frictional force does no work on this yo-yo. So, we need to show that F does no work in order to use the conservation of energy. Right? Because what I'm saying is that this could either be a situation where our initial energy equals our final energy, or our initial energy plus some work from this friction equals our final energy. Right? So we need to figure out which of these two are the correct assumption. Right? I'm going to give you a spoiler alert and say that the work due to the friction is actually zero, which allows us to use this simple top equation. Alright? But I want to demonstrate why. The key here is that the yo-yo does not slip as the string unwinds. When something rolls without slipping, so let's make a simpler picture. Let's say that we have just on flat ground and we have a disc. This disc has some radius r, some velocity v, and we know that at the base of it we have some frictional force F, which is what causes it to rotate with some speed, omega. So we know that the condition for something rolling without slipping is RV equals omega times r. What this means is that if we were to look at a point at the bottom of our disk, so let's go here. At this point, we know that the entire disk moves forward with a velocity v, so I'm going to label this v. We also know that it has, from its rotation, a backwards velocity of, and how about I'll label this in blue and green, of omega times r, which equals v. So effectively at this point, right, at the point of contact, the displacement is always zero because these velocities cancel each other out. So I'm going to make that note that at the point of contact, the velocity, and therefore the displacement is zero, right? And if we know that work is the dot product between force and displacement, at least on the very small scale, right? And then at the larger scale, it becomes the path integral. Well, if this here is zero, then the work is also zero. So that's what lets us come up with the conclusion that we can use the conservation of energy to tackle this problem. Now that we know that, let's go ahead and list out the following. What's our initial potential energy? What's our final potential energy? What's our initial kinetic energy? And what's our final kinetic energy? Well, our initial potential energy, let's go ahead and say for a second that here, right, we're going to say that this potential energy here, U final, equals zero. So if that's our 0 point, then our initial potential energy would be mgl, right? Because you haven't let go of the string at all. We are a height L above this final point where our potential energy is zero. Our initial kinetic energy is simply zero because we're just dropping the yo-yo. So we haven't given it any linear or rotational speed. Our final kinetic energy, we can break into both the linear and the rotational components. So we go 1/2 times m times v final squared plus 1/2 times I times omega final squared. The conservation of energy states that EI equals EF, so UI plus KI equals U final plus K final, right? And so we get the following. MGL equals 1/2 MV final squared plus 1/2 I omega final squared. Let's go ahead and start making some key substitutions. First, let's determine what I for this yo-yo is. So, because this yo-yo is essentially a disk of this radius big R, the moment of inertia for this yo-yo is 1/2 times m times big R squared. We want to solve for the final rotational speed of the yo-yo. Because of that, I want to write V final in terms of omega final. So from here, I need to turn this V final I need to get that in terms of omega final. So in order to do that, all we have to do is note the condition for rolling without slipping once again, which would be that omega final times our little radius r, because that's where the rotation is actually occurring, right? That's where our frictional force is occurring at this little radius r. So omega final times little r equals v final. So v final simply equals omega final times r. I'm going to make these two substitutions now. One for I, one for v final. And we're going to get that mgl equals 1/2 times m times omega final times r squared plus 1/2 times 1/2 m times r squared times omega final squared. Perfect. I will go ahead and cancel out the m's because those appear in all of the terms. I'll go ahead and distribute in this next step as well, so that's going to leave me with GL equals 1/2 omega final squared r squared plus 1/4 omega final squared big R squared. Alright, I'm going to go ahead and take out my omega final squared term, so I'm going to write GL equals omega final squared times 1/2 little r squared plus 1/4 big R squared. And now we simply isolate omega final. So we write GL over 1/2 r squared plus 1/4 big R squared equals omega final squared, right? And to get rid of this square, we simply take the square root of both sides. Yes, technically this is plus or minus, but we recognize that we only care about the positive rotation. So I hope you realize that the key to saying, look, we can tackle this problem using the conservation of energy was to recognize that during rolling without slipping, no work was done by the frictional force F. If there was work done, if this work due to the friction was not 0, that would make this a much more complicated problem. So with that, I hope you enjoyed that little video, and thanks for watching.